Hi, I'm Will Starkey, and this is my Lab 3 for Physics 2212. Start off, we're going to talk about some of the main goals of the lab, which was to find the magnetic field of the magnet, and then based on that, find the dipole moment of the magnet and model it in glow script, and then compare it to the actual data. Some of the fundamentals we are going to use is the Biot-Savart law for finding the dipole moment, and we're going to be using the slope from the Gotten equation, which you will see when we get to the data. A little preview of the results. We got our dipole moment to be 4.85. This was gotten from the Biot-Savart law. And you can see our model. So basic physics principles, as mentioned, was the Biot-Savart law, which is at the top, which we're going to use that to get our dipole moment. The magnitude of the magnetic field from the bar magnet is given by KRN. And then we also need the natural log of the magnetic field, natural log of K plus N, natural log of R. And we're going to use this modeled from slope of our graph to get our K and N values. If we look at the experiment, we can see once labeled, we get a graph which gives us a sloped line of y equals negative 3.3548x minus 13.846. Now, since we know that the slope is going to be equal to n, we know our n value, and we also know our natural log of k, which is going to be our y-intercept, the negative 13.846, which lets us find a k value of 9.7 e to the negative 7. Now, if we use the Biot-Savart law and plug that into this equation, we can find that our magnetic field is 4.85. Now it's time to create our computational model. So first, um, we got our axes and we made our vectors based on the distances to label magnetic fields at certain points, along with calculating our dipole moment in the end. We also had to draw arrows for all of our dipoles at each of those points and calculate what the dipole moments are going to be. Now we can see in the results what we ended up as. We see our vertical parallel and the other ones going parallel, just like how the magnetic field of a magnet should look. Now, some assumptions we made is that the magnets have little to no interference with the surroundings and that the system is magnet while surroundings are fields. Discussion. So for our data, we ended up with our magnetic field at 45 being this numbers right here and the model being this. Now, as you can see, they are different by a slight amount, and this includes some sources of error being interference from other magnetic fields in the data. This was done near a building, so there could have been interference. Well, also, there's not perfectly straight magnetization. If it wasn't at a perfect 90 degree, there's going to be slight variation. So we can see how, while the numbers are close, they are slightly off, especially since the data has a z number and the model shouldn't, which that one has a z number just because there was slight elevation in z magnetic fields, but error happens. Now, what if you did not calibrate your magnet correctly in line with Earth's magnetic field? What would happen to your data? Well, Earth's magnetic field would have then thrown off the measurements because it wouldn't have been in a different direction and therefore unable to compute the actual direction and field of our own magnet. So it would have thrown off all our calculations. Now, why would it be important that if we added another magnet on top of our already magnet? Well, it would double the magnitude of the magnetic field, and then the direction would be the same because the magnet is also its dipole moment of its magnetic field is in the same direction.